Get started. Show of hands. I know there's a lot of computer scientists here. Engineers हैं कोई? Mathematicians हैं कोई? चलो शुक्र है किसी. So the idea of today's presentation is that I know you've had a lot of talks on the nuts and bolts of Python, on computer programming, on that sort of stuff. But this is more of an applied session in which we'll look at how do we actually solve basic engineering computation problems with even a language like Python. Okay, and so the example I'm going to use is electrical engineering, electrical power systems engineering, with a case study of Pakistan's transmission network. जिस तरह उन्होंने बताया कि I'm a consultant for NTDC, National Transmission and Dispatch Company. So there's actually a lot of computation that is traditionally done, which is not done, at least in Pakistan. So I'm going to give you some examples of that. So does anyone have any idea where this transmission line is? This is on super highway, okay? जब आप Karachi से निकलते हैं towards Hyderabad, it's actually not far, before Bahariya town, I think. So you can see that this is actually a double circuit, 500 kilovolts, यानी 5 lakh volt की double circuit transmission line, which is dangerously close to that truck that is, passing underneath. Now, as you can imagine, well, voltage is basically, it's like how badly does, energy want to get out of a certain place. So 500,000 volts is quite desperate to get out of that wire and find a path of least resistance. So if you have any kind of truck which is passing underneath that with any kind of metallic attachment, so it's a good chance the truck will be fried, and of course then there's a massive system failure, and given that this is a 500 kV line, आधा आपका कराची बैठ जाएगा. So no one has actually thought about this, which is what is the distance between this line and this truck, and how does that change over time? Okay, so we can actually compute that. We know, if we know how much power is flowing through this line, and we know what is the property of this line, or we know that when more and more power flows through a line, the line sags. So the more power flows through that line, the more it will sag, and also temperature-wise, there's more heat. In the summer, this line will sag more and more, and eventually it will touch that truck. So we want to find out how bad can it be, and when will it actually do that. So we're going to just go through some very basic maths, some very basic engineering concepts, and I'm going to take you into some Python code. I'm going to show you a couple of libraries that you may have heard of. SciPy, NumPy तो लोगों ने इस्तेमाल की होगी. SciPy unlikely, most लोगों ने इस्तेमाल की होगी. And then I'm going to take you through a case study, ठीक है? Show you exactly how it helps us understand, more importantly, helps the powers that be in Islamabad or Lahore understand what is happening in our system. Okay, so this is just a very quick overview of the different kinds of problems we solve in power systems. The one we're looking at today is basically just a load flow problem. We just want to know how much power is going to flow through different nodes of the network. Okay, there's another problem called optimal power flow, in which we try to figure out what is the cheapest dispatch of different generators such that we can, provide all the load with the power they need. And that's a different problem, and of course there's much more complex problems regarding differential equations and stability and things. So to keep it, within the Python track, so like I said, we'll just look at a couple of those issues today, a couple of those types of problems: basic power flow and optimal power flow. A basic power flow is something that you can solve with a very basic computational technique known as Newton's method or Newton-Raphson, which is a root finding algorithm. आपने शायद किसी ज़माने में मैथ्स में dy/dx किया होगा, उसको ज़ीरो से लगाया होगा और देखा होगा कि इसका क्या रूट्स निकलते हैं, right? That is exactly the same problem. तो इसके जो नीचे जो न्यूमेरिकल सॉल्वर्स हैं, ब्लास है, लापैक है, ये सदियों पुराने हैं, 50s के, 60s के, फोर्ट्रान में लिखे हुए. और then there are newer versions of that, ठीक है, KLU, Paradiso, which look at different matrix factorizations and solve certain types of problems much faster. Like I said, the Python interface is SciPy. There's, you get Newton's method right there. You get linear algebra solving techniques. Sab kuch aapko out of the box milta hai. And then there are the actual, application level libraries that if you know exactly, if you just want to solve a problem like I do, I just put it into either Panda Power or PyPower or Mat Power or something open source usually. Because it's open source, it's free, you can look at the code. A commercial solver like PSSC, which is used in NTDC or in most power companies, will cost you $100,000 a license, okay? Whereas the maths is actually the same. So without further ado, it's very, very difficult to even comprehend. What is this? It's actually very simple, okay? It's any function. Where does it cross the x-axis? Where does it cross 0? F of x equals 0. And then you want to find the roots. Yani, where does that cross the x-axis? How can I find that? So if you take a wild guess, like x0, jo beech mein dikhaya hua hai, well, the solution, which is where it says root x1, is actually wherever you are, plus the difference between where you are and the actual solution, right? And you can find that by taking a gradient, going to where the gradient intersects, going up there, taking another gradient, and iteratively finding the solution. This will find you the solution. This is Newton's method, okay? Almost all of computation is done iteratively and actually uses this technique, or a unbelievably large amount of uses this technique. Okay, some more maths. We won't get through all of this, but the point is just that like I said, if you take your initial guess, you take the distance between the guess and the actual solution, and you expand it, and you drop the higher level terms, you get this little equation at the bottom, which is basically the iterative equation. Okay? Don't get scared, okay? I'm going to explain what this is. This is just the exact same thing in matrix format with multiple variables, okay? So it's on the left, you see I have f of x1, x2, xn, वगैरह, and then there's different functions. f1 is one function, f2 is another function, वगैरह, वगैरह, वगैरह. So you actually get the same derivatives, but in a matrix form, and we call that matrix J, or the Jacobian. Okay, this is important because this is exactly the matrix we're going to solve very shortly. Okay, and you'll see here that shit. I don't want to get through that. It's actually iterative, okay? So you have a once you make the Jacobian, you have a kind of matrix factorization, and then you solve that, and you keep going again and again until you get the solution. Okay, लोगों की आंखें बंद हो रही हैं, मैं कोशिश करता हूँ कि maths को ज़रा avoid करूँ. This is just power flow. It just shows that when you have a transmission line, okay, it has a certain resistance, a certain impedance, and that impedance is actually, it's in the complex plane. Right, so this is the most important thing to understand about AC power systems, alternating current power system. It's not just, आपने शायद class 9 physics में सीखा होगा V equals IR, Ohm's law. ठीक है? It's not just, that R is a resistance, but it's not just about resistance, it's about something called reactance, which is the imaginary, in the complex plane में, it's an imaginary, well, that vector has a real axis and an imaginary axis component, ठीक है? So the real power which you consume, which you actually get billed for from K Electric, that is the power that flows on the real axis, and therefore you get billed for it because you use it to do work. But there's another power, part of that power known as reactive power, which basically just flows in and out of the network depending on the network properties. Okay, so when we look at this, there are two kinds of impedances. One is along the line, and one is between the line and the ground, which is what the first picture I showed you, which is why it's dangerous for a high tension wire to be very close to a truck, because there's capacitance, and that current, that voltage wants to get down to the ground, and that's the resistance that stops it from doing that. Okay, so now that we've seen that, the other thing I want to show is this MVA, right? KVA, MVA, जो आपकी generator की rating होती है, it's in MVA or KVA, right? Volt ampere, which is the voltage times vector times the current vector. Okay, when you expand that, you see I told you it's in the complex plane, so you have that J there. जो maths में I होता है, engineering में J होता है. Where it's the same thing, all right? So there's one component which is active power, which you pay for, and the other component, Q, which is reactive power, and the only person who has to worry about that is the system operator. It's because without that, you cannot actually deliver the P. Without the Q, you can't deliver the P. You don't pay for the Q, but you have to have the Q in the system because you can't get the P without it. So why am I talking about all this? I have a point, trust me. Okay, I'm going to get there. All right, so this is more maths, you forget about this. Okay, शुरू में मैंने आपसे अर्ज किया था कि there's this matrix called the Jacobian, right? This is that matrix. Now we leave the math mostly behind, we start getting into the actual problem. So I told you there's P and there's Q, okay? So this matrix arrangement at the bottom is what we have to solve. We have to try to understand that all our loads, whether it's this university or a substation, has a certain active power requirement and a certain reactive power requirement. And we can serve that, the only way we can serve that requirement is by changing the voltage of the generators, okay? That's the one main way. So when we change, and remember, it's a vector, it's a complex vector, right? So we have the change in the angle, and we have the change in the magnitude. And how that angle changes, we don't have a pointer, do we? No. So how that changes active power, you see, P with respect to active power, with respect to the delta, and P with respect to the magnitude, and also Q with respect to the angle, and Q with respect to the magnitude. So whenever we change the voltage, it has an effect on the active and reactive power, and that tells us ultimately how we are going to serve the power system, okay? So this is what we want to solve. Coming to back to Python, I don't know if this is a good thing or a bad thing, but because now we're bringing a second level of complexity. We've got the power system, and now we've got these functions which you may have never seen. All right, so these are libraries in Python, scipy.sparse. This is sparse matrix library. Okay, so is sparse tells you is a matrix sparse or not. Has anyone heard of sparse matrices before? Okay, so when you have a system like the power system I'm going to show you very soon, most of the nodes are connected to just one or two other nodes. So if there are like 5,000 nodes, you can imagine that the matrix is very sparse, right? And when we want to, well, if you want to solve a matrix equation like this, if you ever try to invert a sparse matrix, the inversion of that matrix is very dense. So you're going to end up with something which is an absolute monster. So you don't want to do that. So you use sparse matrix libraries because they're actually optimized for sparse matrices. Okay? And then there's some CSR matrix which is compressed, sparse row format, and then the H-stack, V-stack just helps you work with that, and then there's the linear algebra package. Okay, so just to scare you a little, I'm going to show you the maths on the left, but on the right you see that the sparse is used. It's actually quite simple, quite easy to use. You just use as matrix, use sparse, and then you basically create your results. Okay, so these two equations on the left, you can see it kind of shows how to, with basic Python libraries out of the box, एक बंदा तो सो गया और पता नहीं ऊपर कितने सोया है, ठीक है, and then so this is just the sparse matrix part, and then just to quickly show you what the Newton-Raphson is, if this actually works. Didn't think this through. So this is really tedious. Maybe I can do this faster on this. Yeah. Doesn't work. Oh, it's stuck. Okay, we'll just go to the next slide. And I'm going to show you after this the Pakistani transmission system. Hopefully, जो सो रहा था वो भी उड़ जाएगा. ठीक है? So again, this is okay. So okay, I don't know how clear this is in the back. क्लियर है? पीछे नजर आ रहा है? पिंक और ग्रीन नजर आ रहा है? ओके। लाल लकीरें जो है ना वो 500 केवी की लाइनें हैं, ठीक है, और ग्रीन जो है वो 220 केवी की लाइनें हैं, और जो एक पिंक, एक्चुअली लेफ्ट साइड पे 2 पिंक लाइनें नजर आ रही हैं, एक ऊपर की तरफ एक नीचे की तरफ, दोज HVDC लाइंस, ठीक है, उनको तो आप भूल ही जाएं। ये तो हमारे मेरे ख्याल से पूरे मुल्क में कोई नहीं समझता है। ये हमने चीनों को दी हुई है कि आप लगाएं प्रोजेक्ट $2.1 बिलियन एंड फिर देखा जाएगा। That's actually how our entire power system works. देखा जाएगा। नहीं, that's nothing as yet. बहरहाल मैं आपको जरा और समझाता हूँ, ठीक है। तो ये हमारे जो अल्लामाओं ने जो पावर सिस्टम पिछले 5 सालों में 10 सालों में जो प्लान किया है, आप देखेंगे नीचे you see these red squares, right? You can see them. These are all power plants. Okay, we have a very north to south power network, which obviously based on our country's geography, and we've got all these power plants in the south, including the one on the left, which is the one that is connected to that line that was sagging and will eventually hit someone, I'm sure. And most of the demand is in the north, and the diagram on the right is actually very similar. It's just that it's more of a what we call a single line diagram. Okay, so what we want to understand is that if we want to operate all these power plants in the south, and we only have limited power transmission capacity through the middle of the country, and all the load is in the north, तो ये सिस्टम चलेगा या बैठ जाएगा, और अगर बैठ जाएगा तो कब बैठेगा, और अगर कब बैठेगा तो उसका हम क्या कर सकते हैं, और क्या अगर हम कुछ कर भी सकते हैं या नहीं कर सकते हैं, और अगर नहीं कर सकते हैं तो क्या वही जो पिछले साल अप्रैल के अंदर जो आधा सिस्टम बेसिकली एवरीथिंग नॉर्थ ऑफ शिकारपुर बैठ गया था, वी हैड अ कंप्लीट ब्लैक आउट लास्ट ईयर, आई थिंक वाज द 28th of May ऐसा कुछ था, ठीक है, एवरीथिंग नॉर्थ ऑफ शिकारपुर वाज ब्लैक्ड आउट. Well, luckily most of you are in Karachi, so you might not have heard about it other than what was in the newspaper, but we want to avoid those kinds of situations. All right, so we want to figure out what's going on. Achha, this is from last month, and this is basically our power generation mix, or at least it was last month. You can see Heidel was about 40%. These numbers are in kilowatt hours, so you could say about 5.6 terawatt hours was Heidel. Coal was quite a fair bit. Gas, and then this regasified LNG. And you know, if you look at the total cost, it was quite significant. This is just the energy cost. This does not even take into account the capacity payments that we pay to generators to just sit there, whether we use them or not. Okay, so just to keep this in mind, if what you want is you want more of the blue, right? Because the blue is the cheapest, and you know, Indus River shukar hai kisi, no one can claim to it, वरना उसको भी claim करते IPPs, उसकी भी capacity payments ले लेते. But we want Heidel to be more, we want coal to be less, and we definitely want the LNG to be less. Okay, so when we model this system, you see that we have within this particular scenario was a 27 gigawatt peak load, peak demand. We have about 28,000 MVA transformer capacity, and when we model this system, we actually have a sparse matrix of 229 by 229, which अगर आप उसको expand करें, that's about 54,000 entries के करीब. But in compressed sparse row, that's only about 1637. Okay, so it's computationally, I can compute this in an IPython notebook. It's not a problem. Okay, so when I actually run this computation, you'll see, okay, so what is the chart on the right? The chart on the right basically is a histogram which shows that these 130 buses, for example, what is the voltage at these 130 buses for the system to remain stable, okay? And NEPRA आपको allow करती है 5% plus minus 5% on transmission. So if 1.0 is your base, you can see most of the actually nodes are actually above what is allowed, okay? And then there's one node, Khuzdar jo hai, that's that's always going to be super low because it's a 300-kilometer transmission line from Dadu all the way to Khuzdar, somewhere in Balochistan. Okay? So that's an outlier. But what is interesting to look at is what are the plants that have actually been dispatching in this. So you see we've got Tarbela at full capacity extension 4, Tarbela 7 to 10, we've got all the coal plants running at full capacity, we've got the 3 RLNG plants running at full capacity. That's 3,600 megawatts of RLNG, okay, which is super expensive. And then we've got a whole bunch of other power plants, and this particular dispatch, then, but you see there's also the Q. So the Q is what is coming out from the Newton's-Raphson algorithm, okay? And it shows, for example, in some, you see the one that is red, it shows minus 4,000. It's not possible for a generator to produce that much. So this is computationally correct, but physically it cannot happen, okay? Now, this is an example just to show you how a very basic engineering problem, which is a very important engineering problem, can be solved with out-of-the-box libraries in Python with a little bit of understanding of how to use sparse matrices and how to solve sparse matrix problems without actually inverting the matrix, okay? So if you actually, this is something that we don't do this in Pakistan. I wish I could tell you that they had a computer in NPCC where they actually had this data and they actually analyzed it and looked at it, but they don't do that. But I am a consultant for the Pakistan transmission sector, and कभी कभार 10 में से एक बार मेरी बात भी मान लेते हैं, सुन लेते हैं, मानते तो खैर नहीं है, सुन भी लेते हैं. तो who knows, maybe depending on funding, if ADB says, okay, out of the $2 billion we are going to lend you, we will require you to do some of these things. Maybe there will be some of these things done in the future. I am working also with the Planning Commission where we are starting to put these kinds of tools in place, and we are looking at Python, obviously. I like to use Python, so we are looking at Python as building the computational kernel, let's say, is tarah ki cheezein. And so, if people are interested, and if there are engineers who are interested, who want to program this kind of stuff in an actual real life scenario, then yeah, feel free to contact me, and we can talk about that sort of stuff. Okay, I think I have another section, but I'm going to end my presentation here because I know everyone is saturated. I want to go back to Django. All right.